different types of continuities there are. So how did you find the discontinuities for number 1? What'd you do? Yeah, well, for starters, you had to figure out where the denominator is equal to 0, right? And when you do that, looking at this, because there's a number in front of the x squared, your mind should jump to, is there a greatest common factor? If there is, it will make your life a lot easier when you go to factor, won't it? If it's not, then it's a little bit harder of a factor, but still most likely factorable. If you look at that and you don't want to factor, what could you do? You could always quadratic formula it, right? If you look at this and you're like, I don't really remember what the greatest common factor would be or how that would factor, it's just escaping my mind, you can always quadratic formula, okay? So what is the greatest common factor here? -4, sorry. So it'll be x squared. This will be minus x and minus 2 equal to 0. All right, x squared minus x minus 2, that will continue to factor, won't it? So two numbers that multiply to be -2 and add up to be -1. What are they? Braden. -2 and +1. Do you agree with him? Yes, no, yes, no? Yes, awesome. So this factors as x minus 2, x plus, that's an x, plus 1, still equal to 0, and you still have that -4 in the front. So what are your solutions? What are your discontinuities? Yeah, 2 and -1. I was like, that's the easy part, right? Once you get it all factored, saying those discontinuities. Does anything come from this -4 in the front? No. What would the -4 have to have if there was going to be another discontinuity? It'd have to have an x, right? So if it's just a constant in the front, just a GCF that doesn't have any variables, nothing comes from that. But if it has an x, then you also have to include 0, right? All right, what about this next one? Once again, discontinuities are where the denominator is equal to 0. How did you take care of this? Close. Difference of cubes. Yeah, difference of cubes. So do you guys remember how to factor with the difference of cubes? Kind of, right? What got cubed for x cubed? X. That's always kind of like a trick question, isn't it? What got cubed for x cubed? Well, it has to be x. And then what got cubed for 27? -3. And I always wait and put my signs on last. Just like in the Google Meet, I always just wait, signs last. So I have x and 3. So the second set of parentheses is based off of the x and the 3. And it's always the same pattern. So you're going to start with the x, and you're going to do x times x. X times x is x squared. And that'll go in the front. And then you'll do the same thing with the 3. 3 times 3, 9. And then in the middle, you're going to multiply these two together. So x times 3 is 3x. And then what do I remember for the signs there? Handy dandy phrase. So on your test, if you got this question wrong, it wasn't because you had the wrong numbers in there or the wrong variables. It's because you were putting in the wrong signs. So be extra careful. So S stands for the same sign as the original. Well, the original has a negative, so this should be negative. Then we go opposite of that, which would make this one a positive, and then AP is always positive, always positive. And you're trying to figure out where this is equal to 0. All right, thoughts? Where'd you go from here? Quadratic formula. You quadratic formula this? Did anybody try to factor it first? Try to factor it? It doesn't work factoring, right? Two numbers that multiply to be 9 and add up to be 3. It doesn't work. By the way, whenever you're doing a difference of squares, these will always have to have the quadratic formula. And did you get irrational solutions? Yeah, and you got one with an I, right? Yeah, complex and irrational solutions. So this will never have real discontinuities, all right? That's just part of a difference of cubes or a sum of cubes. So from here, you could have used the quadratic formula, or you could know that it only gives imaginary solutions. That is just how a difference or sum of cubes works. And we don't really want to know the imaginary discontinuities here, right? We just want to know the real x values because when we go to graph, we only want the real x values. And so whenever you're doing this, you can know that this quadratic from the sum or difference of cubes is only imaginary solutions, so there's nothing you have to do to continue that. So there's only one discontinuity here, and it is at x equals 3. One discontinuity, x equals 3. Yes?
So I did it a completely different way.
Yeah.
That's the same thing. It was like,
Did you add 27, and then you took the cube root, and that gave you this one? That will work. However, you missed out on whatever could have been here, right? So as long as you know that it has a real solution, but it also has imaginary solutions, because given the type of question, I might just be looking for imaginary as well to be included. So if you do it where you add the 27 and cube root, you'll get the real ones, but you won't have access to the imaginary. But yes, that would be an okay method to get this real value. Yep. As long as you obey all the rules of math, right, then you're good. All right, what questions do we have? Anybody have any questions about discontinuities, how to find them? All right, so today we're going to talk about what types of these discontinuities are. So x equals 3 is a certain kind of discontinuity. If you go back to the last one, -2 and -1 are certain kinds of discontinuities. And so depending on what's going on in the numerator will impact the kind of discontinuity that we have, okay? So we're going to talk about exactly what's happening. All right, so here's number 3. We're going to find all the discontinuities and we're going to classify them as what they are. You ready? All right, so to start off, we're going to have to do some factoring, right? If the denominator is equal to 0, then it is a discontinuity, right? All right, but when we're comparing the discontinuities, when we're trying to figure out what kinds they are, you also have to pay attention to the numerator as well, all right? So if you're trying to figure out not just what the discontinuities are, but the types, you actually have to factor both the top and the bottom, all right? So instead of setting it equal to 0 and factoring just the bottom, we're just going to rewrite the rational, and we're going to factor both the top and the bottom, okay? All right, which one would you like to factor first, the top or the bottom? The bottom, because it's the easiest? Because it's a difference of squares. So x plus 3 and x minus 3. And then now you have to mess with the top. What should we do on the top? There's a greatest common factor there. What's the greatest common factor? -2. And what's left over would be x squared plus 2x minus 3. Not completely done factoring in the numerator, right? So I'm going to make another fraction. Let's keep going in the numerator. We're looking for two numbers that multiply to be -3 and add up to be +2. Yes? -1 and 3? Do you all agree with Shannon? -1, 3? All right, so then the numerator would be x minus 1, x plus 3. Don't forget the -2 in the front. It is there, right? And then your denominator is x plus 3 and x minus 3. When it is all factored, then we can not only say what the discontinuities are, but we can say what kinds they are. And guess what? We can also really easily find the x-intercepts. So we're kind of throwing that in today as well. So what do you notice about the numerator and denominator? They both have an x plus 3. Perfect. So circle the x plus 3s. You have a match, right? You have a match. So there is a discontinuity at -3, because if you put -3 in, you're going to have 0, and on the top you'll also have a 0. So there is a discontinuity there. And what is happening is there is a hole in the graph. a hole. So your graph is going along, la, 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 and it gets to that point, wherever that point is, and there's literally a hole. So it's like la, 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 hole in the graph, and then it just keeps going. All right, so what's happening is your graph is just going along, all of a sudden, bam, there's a point that you can't have because it causes you to divide by 0, and it is just a hole in the graph. All right, hole, yes, question?
No, it's more an easy way to explain it. Basically, if I were to explain it now, it's people were able to go into stores and buy things, and then COVID happened, and you couldn't go into stores for days, and then so nothing was being sold, and then it continues afterwards.
There you go. So this is like the COVID of the rational function. All right, I like that connection. Yeah.
What is the purpose of this? Like,
So what we're going to do is we're going to graph these. And so when we're done graphing them, we'll have to pay attention to where we have issues in our graph. So there's holes. A hole is what we call a removable discontinuity. And so because it's in the top and the bottom, it just makes a little hole in the graph. And it's something that when you move on into like pre-cal and calculus, that those are issues that you can take away. So remember how we can't divide by 0, right? Well, if there's a hole in the graph, it's a workaround for a dividing by 0 issue. All right, but our end goal for this class is to be able to draw a graph of these.
but I have to do more after this class.
Yeah, and we'll do more rational functions after this class as well, yes. We'll see them a ton in pre-cal, calculus. Right now you're getting the intro and the graphing aspect of it. All right, so if the factor matches in the top and the bottom, if you have a match, then there is a hole in your graph, right? So if you were like drawing a line and there was a hole, then you would just keep going, all right? Or maybe you had a quadratic and there was a hole, then you would just keep on going. So you're drawing a graph, and if there's a match because there's a divide by 0 issue, but it also causes the top to be 0, just a little hole in your graph, all right? All right. What's the other discontinuity? Oh, wait, hold on. There's a hole. We're going to say where is it at. The hole is at x equals -3. It's what makes those factors equal to 0. So your hole is at -3. Where's the other discontinuity at? It's at +3. And that's from this guy, right? Right here. And so if it's an issue with a divide by 0, but it doesn't have a match in the top, it's what we call a vertical asymptote. Yes. How many of you have heard of asymptotes before? No. Is that a no, I've heard of them, I just really don't want to talk about them again? Oh, you've never heard of it. It's a vertical asymptote. Yeah, and it literally, you call it an asymptote. I know it's a crazy, unique math word, but yes, vertical asymptote. And that's if it's in the bottom by itself and there's no matches in the top. And this vertical asymptote is at x equals +3. And here's what happens on your graph in a vertical asymptote. You're going to have a vertical dotted line, and your graph is going to come up to the line, and it's going to go either up to infinity and just get closer and closer and closer and closer to the line as it goes up, or it could come in and it would go down to infinity, -infinity, and it would get closer and closer and closer and closer, but never ever get there. So a vertical asymptote is going to be a spot in your graph where your graph either takes off going straight up or it goes straight down, and it just keeps getting closer and closer and closer, but it never actually gets there. So the closer you get to a vertical asymptote, the closer the line is, but it's never actually going to get there, all right? So imagine getting slightly closer to something, and just a little bit more closer and closer and closer, and you can always get closer without actually getting there. All right, vertical asymptotes. We're going to talk about them for probably like the next week and a half or so. So if your mind's blown right now, it's okay. All right, and last but not least, x-intercepts. Does anybody have any guesses? I haven't said anything about an x-intercept so far, except for literally right now. Any guesses where the x-intercept is? It's on the graph, yes. It's the numerator, yes. What's the one in the numerator? So it would be x minus 1. And so your x-intercept would be at positive 1. Yeah, this right here gives you the x-intercept. And it's at x equals positive 1.
So it's just the one.
Just the 1. It's not the negative 3. Why is it not the negative 3? Because what's on the graph at negative 3?
It's a hole.
It's a hole. And if it's a hole, it can't be an x-intercept. So if you have a match, it's a hole in the graph. If you are in the denominator, it's going to cause a vertical asymptote in the graph. And if it's in just the numerator, it will make an x-intercept for you. So by doing a little bit of factoring of the numerator and denominator, we can actually tell 3 things about this function. We can tell the x-intercepts, the holes, and the vertical asymptotes. All things that are going to be important when we go to graph these functions. All right, you ready for the next one? Oh, this one's not too bad. Look at this. It is a rational function, right? Because there's one in the numerator, there's a polynomial in the numerator, polynomial in the denominator. They're both lines though, aren't they? So what does that mean in terms of factoring? There's no factoring here, right? So because there's no factoring, guess what? You're good to go ahead and just say where the issues are, all right? What's the holes, what's the vertical asymptotes, and what are the x-intercepts? So if it doesn't factor, it's actually easier. You save all that work in between. All right, the x plus 3. Does it have a match in the numerator? No. And if it doesn't have a match, what is it? It's a vertical asymptote. You may identify them as VAs. You do not have to write vertical asymptote out every single time. Unless you don't know what VA stands for, then you should write it out until you got it in your head. But yes, you can say that there's a vertical asymptote. And where does it happen at? X equals? Negative 3. You always are changing your signs, right? It's always what makes it equal to 0. Are there any holes? No. Holes only happen when you have a match in the top and the bottom. If you don't have any matches, then guess what? You don't have any holes. So there are none. No holes in this graph, just a vertical asymptote. Are there any x-intercepts? Is there anything in the numerator that didn't get used? Any variables in the numerator? Yeah, this 2x, right? The 2x, and so the 2x is going to make a x-intercept because it wasn't included in any holes. It didn't get used for anything else. And that would be at x equals?
Does it matter that there's a negative?
No, this isn't going to matter for us. Nope.
Negative.
So where is the x-intercept? What makes 2x equal to 0? 0, right? 0. If there's nothing added or subtracted, then it's at 0. Oh, does it ask for that as well?
Yeah.
Okay. We'll do it for this one. Sorry. We'll do it for the rest of them. We missed that last one. So then what's the y-intercept? You did that in your homework / we talked about that yesterday, right? How do you find the y-intercept?
Zero.
Plug in 0, right? For x. So if you put a 0 on the top, you'll have 2 times 0, which is 0. If you put in 0 in the bottom, you'll have 0 plus 3, which is 3. And 0 divided by 3 is 0. So your y-intercept is also at 0. Yeah. Exactly. If your x-intercept is at 0, your y has to be at 0. So because you knew this, you could have just said, oh, hey, the y-intercept is also at 0. Yeah. If not, though, if you don't remember that or you just don't recognize it, you can always just plug in 0. All right. Next one. We have a cubic on the top and a quadratic on the bottom. So in order to figure out where all this stuff is, we do have to factor these, don't we? All right, so let's go ahead and do some factoring. Would you like to factor the numerator or denominator first? Denominator. All right, how do we factor the denominator? GCF, right? What's the GCF? 4x, perfect. Left over would be an x minus 4. And then the denominator's done, right? What about the numerator? There's a GCF there as well, right? All of those terms have a x. And left over would be x squared minus 4x plus 3. Is the numerator done, or do we have to keep going? You have to keep going. So we're looking for two numbers that multiply to 3 and add up to be negative 4. 1 and negative 1 and negative 3?
Yes.
Is everybody okay with that? Negative 1, negative 3? You've done a ton of factoring, right, like that? So there's still the x in the front, x minus 1, x minus 3. And then I'm just going to transfer the info about the denominator. So I'm looking at one fraction right there. All right, any questions about the factoring that we did? So we've seen all this factoring before, right? Just instead of as a fraction, you've seen it just as individuals. So yeah, hopefully you remember a little bit about factoring. It's gonna make this easier. All right, so let's start with, you wanna start with vertical asymptotes or you wanna start with holes? Holes, all right. Do you see any holes? Because it is possible to have none, right? The last question we didn't have any. See any holes? Yes, got them. Where do you see the holes?
0.
At 0, because both the top and the bottom have a x that has nothing being added or subtracted to it, right? Even though there's a 4x in front of that one, it's still technically, both of them are zeros at 0, right? And so there is a hole at x equals 0. Are there any other holes? Because you could have more than one. You could have tons of holes. You could have no holes. Any other matches you see? No more matches? All right. There's no more matches. Then we can move on to the vertical asymptotes. We'll do that one next. Where are the vertical asymptotes going to be at? At 4. That's the other one in the denominator that didn't have a match. So vertical asymptote at x equals 4. All right, and then you have x-intercepts. And the x-intercepts are just really nice. They kind of just fall out because you've already done all the factoring and taken a look at everything. So where are your x-intercepts at? 1 and 3. Those are going to be your factors in the numerator that don't have any matches. Remember, if it has a match, it's a whole, and it doesn't qualify as either of the others. So x-intercepts 1 and 3. All right, and last but not least, we do need to find that y-intercept. Thanks for reminding me about that. Oops, hold on. All right. Y-intercept. So I can't see. There we go. Okay. And how do you find y-intercept again? Plug in 0. So if you plug in 0 to the numerator, you're going to have 0 minus 0 plus 0. Which is 0. In the bottom, you're going to have 0 minus, which is also 0. 0 over 0, we would say, is not 1, not 0. Undefined, because you can't divide by 0, right? So this is undefined. And Shannon, you were saying earlier, why is it undefined? Because what's happening? There's a hole at 0. So if there's a hole where x is 0, that means that there's a hole where it's supposed to cross the y-axis. So it doesn't cross the y-axis because wherever that would happen, there would actually be a hole. So for example, if you had a graph and it was going along la 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 and it was going to hit your y-intercept, you'd be like, whoops, hole in the graph, and then it would keep on going. So if there's a hole at 0, then there aren't going to be any y-intercept. You can't have a y-intercept. All right, how are we doing? Is everybody okay still? Okay. All right. How many more do I have to practice? One more. I'm going to let you try it on your own then. Give it a shot. We'll go over it, but let's see what you can come up with. Did you all start with the numerator or the denominator when you factored? Denominator, numerator, numerator. It really doesn't matter, right? You can start with either one. Sometimes you like to take the hardest one, get rid of that one first, right? Or sometimes just the easier one. So let's go ahead. We'll start with the denominator. What'd you get for the factors in the denominator? Because that was a pretty easy factor, right? Plus 2 and plus 3. So x plus 2, x plus 3. Do you all agree with that? Yes, two numbers had to multiply to be 6, add up to be 5, so they were 2 and 3. 2 times 3 is 6, 2 plus 3 is 5, right? Everybody good? Okay, numerator, a little bit harder to factor. How did you factor the numerator? By grouping, right? So you had to group the first two together and these two together. And so either you can kind of keep it in the numerator, or if you want to like factor off to the side and then just put your solution in the numerator, that's fine as well. However you want to kind of take care of this. Sorry. This is super annoying. There we go. All right, so in that numerator, you took out an x squared first, right? You had x plus 2 left. And then you took out a negative 9. And then you also had x plus 2. I ran out of space a little bit, but x plus 2. So then your factors would have been x plus 2 and x squared minus 9. Is that correct? Yes? Yeah. And then technically, there's a difference of squares. You should recognize those, all right? We've talked about them a ton. Start recognizing those difference of squares. X squared minus 9 is a difference of squares. So it factors as x plus 3 and x minus 3. All right, so we have x plus 2, x plus 3, and x minus 3. All right, so tell me what you found. Holes, you want to start with holes? What'd you find for the holes? Negative 2 and negative 3, there are 2 of them. There's a match here, right? And there's a match there. So you have 2 holes. Both of them have matches. So they would be at negative 2 and negative 3, 2 holes in this graph. Vertical asymptotes. Say that again. There are none, right? There's no extra factors in the denominator that don't have a pair. So that means that there are none. X-intercepts. Somebody said 3. That would be from this factor in the numerator, right? So it's at x equals 3. And then last but not least, find that y-intercept like what we were working on yesterday. And the y-intercept, where'd you find it at? What was it? It was at negative 3. And that actually came from negative 18 over positive 6, right? So all these would be 0, so you'd have negative 18. These would be 0, so you'd have 6. And negative 18 over 6 is negative 3. All right, what do we think? Super crazy, not super crazy? We're kind of gearing up for this graphing, so we're trying to pull some important information. All right, there's kind of one more piece of important information that we haven't talked about yet that we're going to talk about on Friday. And it's another kind of asymptote. So instead of a vertical asymptote, what we're going to talk about is a horizontal asymptote. So on Friday, we'll go over some horizontal asymptotes. And then next week, we're going to put it all together and we're going to work on graphing these things, all right? All right, before you start your assignment, I kind of have like a summary of how to find everything at the bottom. I can make it down there. There we go. So let's just summarize in general where all these things come from. Maybe this board doesn't really like me very much, does it? There we go. Okay. Here. All right, so how do you find a y-intercept? Set x equal to 0. Plug in 0. It is possible to have a y-intercept. It is possible to not have a y-intercept, right? Right? We've seen a problem where we did have a y-intercept, but then we also saw one where we didn't. So it is possible to not have a y-intercept. How do you find holes? Right, so you have matches in the numerator and denominator, right? The first thing that you have to do, though, to find these things is you have to factor, right? So maybe in the front, put that factor top and bottom, and once it's factored, then you can go ahead and say what these are. In the holes, there was matches. So your holes, you had matches. Where'd the vertical asymptotes come from? The ones in the denominator that did not have a match, right? So these come from the factors in denominator. And I am going to add with no match, because if it has a match, it's a hole, right? So you always find your holes first. It's easier to pick out your matches, and then kind of what's left over gets distributed to either your vertical asymptotes or your x-intercepts. So the x-intercepts are which ones? Factors in the numerator without matches. The nice thing is if you're going to find the holes, you already will be able to see the vertical asymptotes and the x-intercepts, right? If you're going to find the x-intercepts, then you would also be able to see your holes and your vertical asymptotes, right? If you're going to find vertical asymptotes, then it's really easy to see the x-intercepts and the holes. So these three things all go hand in hand. If you're going to find one, you can find all three just as easy, right? And that does not happen very often, does it? Normally you have to find one thing, and then you look for something else for another thing, and then you're over here for the third thing. These three are nice because they all go hand in hand. All right, any questions that you have for me? No? Okay, so that's all that I have for you.